Okay, let me begin. So
Okay, let's go.
my name is Maksim Tumashov, and today my topic will be dedicated to the theoretical and experimental study of angle-dependent metasurfaces. Actually, previously I did this this speech, but it was like unfinished, and today I would like to expand it a bit, and I hope you were on the seminar I took previously, but it is not bad if you don't. So firstly, I would like to talk about angle independent metasurfaces, actually plot twist, because it is a very common for researchers to search to find devices which exhibit a very low angular response from the structures, because usually it is required for a device to operate under different under different angles with the same performance. So usually people seek for angle stable devices. And as an example, I picked three designs which are demonstrated here. As you can see on the left side, it is an optical absorber which consists of metallic nanodiscs placed on the substrate. And from this map below, you could see that actually it absorbs power with the coefficient near unity. The red one corresponds to unity absorption in dual band. And also there was an additional research for angular stability of this device, and it was found that actually for the angles up to 50 degrees, the device has a very strong response, and it is very stable itself. The second device I would like to demonstrate to illustrate the principle. It is also an absorber, which is designed to operate in gigahertz frequency range, and it consists of metallic rings, and as you can see from the absorption plot here, it absorbs all the power one through three different frequency, and there is also research for angular stability. So the team changed the angle of incident field from 5 to 50 degrees, and as you can see, the angular dependence of the structures, so its dependence on the incident angle is negligible. So this device is also very strong in this sense. And the third one is also for optical applications, and it is a metasurface which acts like a frequency selective surface, and as you can see, it also has a very weak response to the incident field. So it means that you can actually impeach field from any angle you want, and you ensure that the response of the structure stays the same. This is very practical. This is very good. But let's let let us consider a different case when we can have angle-dependent devices. So what does it mean? It means that the device experiences a different behavior under different incident angles. So it means if we illuminate the device from, for instance, angle 0 and angle 30 degrees, its response will be different in every case. And so this property may be utilized as the additional degree of freedom. And actually, this is a very huge field to study. And many researchers seek for such devices which allow to combine different functionalities supported by only single metasurface. And for instance, here I found the works. First of them is for seek for a device of angle selective beam deflection. So it means under different incident angle, you may expect different refraction or maybe deflection behavior. And the second one, so such metasurfaces may be used as multifunctional meta devices, like you may illuminate it with the linear polarization, as it demonstrated here, under angle of, for instance, 30 degrees, and expect that it transform the polarization to the right circle polarization. And if you use a different angle of illumination for the same polarization state, I mean, a linear one, you'll expect the different transformation of the polarization. So polarization in the output will be a left circular polarization. Also, there are also application of such devices as resonant frequency shifters. So it means when you illuminate it from one angle, you expect the resonant frequency to be to be one, and if you illuminate it from another direction, you expect to see the shift in the resonant frequency. And this is mostly what I'm going to tell about you today. So it is very convenient. Also, let me jump a bit to using resonant structures for the sensing. It is very common to use the resonance structures for sensing, because sometimes they allow us to concentrate the electromagnetic field in a very small area, which allow us to obtain a very dense field distribution at some region. And this may be used to precisely detect some properties of materials. For instance, Team Gupta made such a metasurface which consists of eye-shaped elements. And if you can see on the resonant frequency, the field is strongly concentrated near the gaps between two metallizations. And if we apply analyte layer on this surface, we will expect that we will expect different resonance response. So here they are deposit different analytes on this type of structure with different refractive index. And as you can see, the shift in frequency may be very significant, which may be applied to detect which material do we compose, or some of its properties. But the disadvantage of this approach is that it requires spectral measurements, actually in a very wide band. As you can see, it is almost terahertz frequency range, and for some laboratories, it may be challenging. Another big branch of sensing is the thickness sensing. So I picked the design, which was made by Team Nikolaev, and it is also a metasurface composed of honeycomb-like unit cells. And as in previous case, the field mostly concentrates in the gap between metallizations. So if we apply an analyte layer, we will expect the change in dielectric permittivity in these regions, and then it will lead to change in capacitance, and also it allows us to see the shift in the resonant frequency. And this team was, I think, the first one who proposed to use the angular dependent devices to detect thin films, because as you can see here we have a plot, a transmission coefficient peak versus incident angle, and for every different analyte thickness, we'll see the resonant peak is on its own angle. So it means for so we could see a huge difference between, we could distinguish layers up to 0.5 microns at least. Yeah. Then, based on these works, combined all the knowledge, we propose our design, which was previously demonstrated to have angular dependent properties. So it means that it has a strong dependence of resonant frequency versus the angle of incidence. And this device was proposed for single frequency sensing. It means that we could only have a source operating at single frequency and still sense some films applied on this device. And to illustrate the principle of operation, I would like to separate it on three stages. First one, it is like a response of the device under normal incidence without analyte, mark it as one. The second stage is the normal incidence with analyte, when we have some deposition of an additional layer, properties of which we would like to inspect. And the third one is the oblique incidence with analyte. It means that we rotate the device to bring the resonant frequency back and see which angle we need to bring it back, actually. And the operation of the device may be illustrated with the dispersion relation of such structure. So previously, yeah, the axis is frequency and the transverse component of the k vector. So the dispersion relation of this structure is illustrated here as a red curve. And in the case if we apply the additional layer, we may expect that this dispersion relation will move in the direction of lower frequency. So yes, and to compensate this frequency shift, we would like to rotate the device, and as you can see, for some incoming wave, so regulating its slope in terms of dispersion relation, we could find the position of initial frequency. So in more simple words, we have a normal instance without any applied layer. So we have its spectral response. Then we apply some layer, we experience some frequency shift in position 2. And after that, we could rotate the device to shift this spectrum to the initial position. And the angle that we need to be applied is in strong dependence of material properties. So firstly, let me illustrate the operation of the device by illustrating its charge distribution. So let us imagine that we illuminate the device with a T wave, and we will expect this kind of charge distribution along the metallic strips. As you can see, this may be represented as small capacitances, actually. So yeah, we have some region between positive and negative charges, which may be treated as capacitance. Also, we have a capacitance between a set of nearest strips. I mean, nearest group of strips. And we also should have some self-inductance for the metallization. So it pushed us to the thought that we may make some physical inspired equivalent circuit for this design. And actually, it is demonstrated here. So as you can see, the capacitance C1 correspond to the capacitance for this capacitance between the group of strips. L is corresponding to the self-inductance, as I said previously, and C2, it is the capacitance between nearest adjacent strips. So in this region. Also, since this structure exhibit the phase shift on the input with respect to output, we also should introduce some phase factor for the current which flows through the unit cell. Then applying Kirchhoff's law for this circuit, it is possible to retrieve circuit admittance of such circuit, which also may be converted to the impedance just inversing the admittance. And knowing impedance, there is no problem to retrieve resonance condition for this circuit by setting the impedance to 0. And the resonance condition for this circuit is presented here. Let me move to more simpler things. So the equivalent circuit that was presented on previous slide may be simplified to this more general, simpler circuit, which correspond to the normal incidence only. So in case of normal incidence, we have no phase shift for currents on the input and the output sides of the unit cell. And then it is possible to make the circuit looks much simpler. So in total, we have 4 different parameters which characterize this device. Also, I forget to say about the capacitance of the substrate. It is also an important factor. So it means that the substrate itself also has some capacitances and capacitance, and this capacitance is connected to the parallel to whole circuit. So again, we could find an admittance of this circuit, and to predict numerically the physical response, we would like to have 4 different constraints. So to in the end, we'll have 4 unknown parameters, 4 unknown circuit parameters, and 4 constraints, which allow us to easily retrieve the circuit parameters and then predict the spectral response of such unit cell under oblique illumination. So 4 constraints are illustrated here. Here we have first constraint is the derivative at frequency goes to 0 at this region. So to find the circuit parameters, we also have to do at least 2 numerical simulations, one for the normal incidence, and the second one is for arbitrary oblique incidence. So in the case of derivative, we have it expressed as the like analytical expression, and we also have some numerical results, so we could equalize them. The second condition is the resonant frequency itself. So it also may be easily retrieved from the simulations and from the equivalent circuit. The third one is the frequency of transmittance deep. So it corresponds to the maximum of reflection, actually. It also may be found from the numerical simulations, but it also has an analytical expression. And the fourth one is the ratio of capacitances. So all parameters included here is also may be retrieved from the simulations under normal and oblique incidence. So in total, to predict the angular response of such design, we have to make 2 numerical simulations and write some system of equations that has a solution, as I will demonstrate here. So actually, it was found by us that using this conditions, it is possible to predict the spectral behavior of such unit cell with a high accuracy, up to 80 degrees of illumination. Yeah, to go from the impedance to the transmittance coefficient, the boundary conditions may be written, but I omit this to save some time. But actually, there is a straightforward relation between the impedance of the cell and the transmission coefficient. So here I presented firstly the theoretical response. By theoretical response, I mean that to simulate this, the structure, the thickness of metallization was considered to be 0, and materials assumed to be lossless. It is just like a first prop for us to see if the model is working as we expect it to be. And as you can see, just by 2 numerical simulations for 0 and 20 degrees, we could predict the angular response of the structure for much for the angles much greater than 20. So with some accuracy, it is even possible to predict the response near the 80 degrees. But of course, the most precision is achieved on the range of small angles. The possible discrepancy between the results that we observed here for the case of 80 degrees is because some circuit parameters actually are angle dependent. So it means when we rotate the design, we could expect that some efficient value for capacitance or for length of the strips may be changed, and we didn't include it in our calculations. Then this model was the circuit model we proposed was modified to support some resistive losses that we unavoidably have in our experimental sample, and to introduce the ohmic losses, yeah, the only thing we have to do is to add a resistance in series with the inductance. So in terms of equations, it means that now our inductance is complex, consisting of two parts, one for active part and one for reactive part. And here you can see the comparison of measurement simulations and the circuit model. And you can see that coincidence is pretty well here, even in presence of ohmic losses. So it means that this circuit model at least works for the design we analyzed. So this approach may be extended to the case of the presence of the analyte. So loaded case means exactly that an analyte is applied, deposited. And to do that, we have to modify resonance condition that was obtained before. The modification that we need to introduce is to introduce some functional dependence of capacitances C1 and C2. And it easily may be done. And then the only thing to do is to express the required incident angle. So when it's done, the interesting fact occurs that actually this angle may have like a linear dependence on square root of thickness with some proportionality coefficient alpha. Another important parameter that we have to analyze is sensitivity. So the sensitivity is the parameter that characterizes the device performance. And for us, we define sensitivity as the ratio between the required rotational angle and the applied thickness. And if we take the derivative from here, the simple equation may be retrieved for the sensitivity. Yeah, so in our case, it means how the angle changes with the change of the analyte, of the thickness of the analyte. The experimental investigation was also done. Here I demonstrate two cases for two thicknesses. Here we see the first one is first thickness is almost 0.5 microns. And you can see that if we fix the frequency 0.139 terahertz, we need to rotate the design at the angle of 27 degrees to bring the resonance back. And this value of 27 corresponds to exact thickness, which may be obtained from, for instance, numerical simulations. So some kind of calibration curve may be also done, like theta versus thickness, for instance. And therefore, this device may be used for some practical issues. The second case is the case of the thickness is almost 1 micron. As you can see, the angle here is dramatically different, like 7 degrees difference, which means that this device may distinguish thicknesses below 0.5 microns at least. But I say it like 0.1 microns even. So it seems to be very sensitive to the applied layer. Then we repeat some this type of measurements for different thicknesses, like in the range from 0.4 to 1.2 microns. And here we also, besides the experimental and full wave simulations, we also demonstrate here the straight line, which corresponds to the expected linear behavior obtained from our circuit model. And you can see for smaller thicknesses, it fits better than for large ones. But I think there is a way to improve circuit model somehow to achieve the good correspondence even for thick layers also. Also, it would be interesting for us to make measurements for like in this region for thicknesses below 0.4 microns, but it is hard to do from the technological point of view. But someday maybe we will. So this is all from my side. Thank you for attention. If you have any questions, please go on. Thank you.
Okay, dear colleague. Okay, Muhammad has a question.
Yes, thank you for your presentation. Sorry, I couldn't spelling well your name. So I'm sorry about that. But
It's Maxim.
Maxim. Okay, Maxim.
Maxim.
Yes, hello, Mohammed.
Thank you, Maxim, for your nice presentation. So my question is, I didn't see your motivation working in the terahertz range.
Mhm,
So could you please explain a little bit more what is your motivation to design and making a model
mhm,
and as well as your experimental setup? Yeah, like what is your motivation to build a sensing platform in terahertz region?
mhm.
Thank you.
Yes, thank you for the question. The motivation to study thin films in the terahertz range has many. So the main advantages to use terahertz frequency range, because it is a well-studied range to do such research. Like many biological films is studied in the terahertz, because terahertz is non-invasive, but it allows us to go deep to the some issues. And also, if you consider the, like, for instance, human issues, it also may be studied through terahertz frequency range. And this is a quite common range to study, to work with, because it is very, how to say, secure and well studied. And also we have already a source operating at terahertz, and so for us, there is no other choice, I think. Yes, because, and also our aim is to replace convenient um, uh, like time domain spectrometry methods and others which require bulky setups, usually with many components to be um, fit with each other. But the setup measurements that we need include only the source of the excitation, the sample itself, maybe some lenses to focus the beam, and the detector. no manipulation with the phases and so on, which is very convenient to do such measurements. But we aim to make a cheap, simple device to do measurements which may replace convenient approaches using interrogers. Yes.
Okay. I hope that Mohammed is satisfied with this answer. So, any other questions? So, Maxim, you mentioned that the other approaches, the alternative approaches, are less easy in comparison to this. So, what are the other approaches? Other ways to do this?
It is frequency domain spectrometry, I think, and time domain spectrometry. In my previous presentation, I analyzed
in
them.
which range? In which range? Because you told that terahertz are not invasive, so I think you meant not ionizing and so on.
Yeah,
so,
yes. So sorry, I mean in this sense, sure.
Yeah, and the other approaches, are they in the ionizing range?
No. They are using the same frequencies, but just from the setup point of view, they are very bulky usually. And they require to measure. They require measurements in the some frequency range, and some of them require to phase measurements, which is not simple every time. But our approach require only the magnitude of transmission measurements, and this is much simpler to organize, to deal with.
Okay. Maybe more questions from our listeners? Okay, guys, we need to ask because it will be very useful for Maxim.
Okay, I can ask a question.
Great.
Can you show me the 8th slide? Oh, the next one, I guess. So, sinus theta naught is proportional to alpha square root of h.
Yes.
But if we look at the expression in the left, c is a function of h. So maybe c is a nonlinear function of h. And in this way, sinus is not proportional to square root of h, no?
Yes, I have to explain here a bit. So this equality was obtained in the suggestion that the capacitance is linearly changed with the applied thickness. So the thicker layer we have, the capacitance is also changed linearly. And about the linearity, to obtain this kind of equality, we have to apply a Taylor expansion to this function to keep only the linear terms. But it was found by us that the other terms is not that significant as the first linear one. And then we assume that we could keep this equality linear.
Okay, thank you. But you said that you have some problem with the thick examples, yes? Maybe it's because of that?
Yeah, sure. It may be the reason, but as I
Not
said,
the main reason.
Yes, but as I said, maybe we should assume some nonlinear behavior of capacitance also to deal with the thicker layers. Oh yes, this is a very interesting and promising topic to start to study, and maybe somebody would like to participate to expand this theory to analyze different angle dependent designs.
Thank you.
Mm-hmm.
Okay, thank you very much.
Thank you.
Any other questions? So since I don't see any more questions, we can, I think, finish now.
Mm-hmm.
And thank you very much for your presentation.
Yes, thank you
Goodbye.
for participating. Yes, see you next time. Goodbye.
Yeah, see you next week. Goodbye.